Alright, so what are rational functions? So rational functions are quite literally just a division of polynomials. So it's like a fraction with one polynomial over another. And they're characterized for having both horizontal and vertical asymptotes in a lot of scenarios. At this level, we're just looking at rational functions with polynomials in a linear form. So general structure you'll see for this is something like ax plus b over cx plus d. By analysing the actual function we're given, you can look at the different elements to find both the vertical and horizontal asymptotes. So the vertical asymptote is found by specifically looking at the denominator. So when cx plus d equals 0. So when the denominator equals 0, and then what you would do is you'd rearrange it, moving the d over there, dividing it by the c to find at what x coordinate will y equals 0, so your vertical asymptote. And then for horizontal asymptotes, we follow a slightly more difficult process. So let's just have a look at one scenario. So we've got f of x equals 2x minus 6 over x plus 1. And so first is we're going to find the asymptotes. So we've got this function, and what we are going to do is we're going to rearrange it slightly. And we want to bring the denominator into the point where x is. So what I'm going to do, and that might sound a little confusing, but what I'm going to do is put 2, and then I'm going to put the denominator in, which is x plus 1. And then and so we've got the same number of x's, so that's completely fine. But what I'm going to do is, obviously, originally we had -6 up there, and so we need to make sure that still applies, because what we've just done is we've added 2, so I'm going to do -8, and then the numerator still gives us -6, and then obviously the denominator will stay the same. And then what we can do is, this is where it gets pretty cool, is we can rearrange it, and because we've got this like this, is I can cancel this part out. So I can cancel for this section, you can see that these two can cancel because they're common. I'll just get rid of that so we can try this again. And so we'll have -8 over x plus 1 plus 2 because we've cancelled that. And so then what we can infer from this is that we have a horizontal asymptote at y equals 2. And then we know vertical asymptotes are pretty easy to find, so we just say, have a look at it, when x plus 1, so when the denominator equals 0, therefore when x equals -1, so cool, we'll just get rid of that, like that, and then we can just say, and vertical asymptote at x equals -1. Easy. Alright, and now what we're going to do here is we're going to talk about the behavior as x approaches different parts. Where does y approach? And so you can either use a graphics calculator to graph it and go, oh, okay, as this approaches this approaches this. Or the second option is just to create a table and talk about all the different values and talk about where it approaches. But what I'm going to do is I'm just going to consider our horizontal and vertical asymptotes that we have there. And so I'm going to say, as x approaches -1, and as y approaches 2, so the horizontal asymptote and 2. And the reason I write it twice is because it can approach it from the negative and the positive side in both scenarios. And so then what we can do now is I can look at the graph on a graphics calculator just to make it easier for myself. And what I'll do is I'll just give you a little bit of a peek at what I'm looking at. It looks a little bit like this, and we've got that, and we've got crosses over there into there. Now, I don't know the points, but I just know what way it's going. And so what I can infer is that horizontal asymptote along there, and vertical asymptote along there. And so what we can say is, I might just do this in red to represent it, as x approaches -1, so as it approaches this vertical asymptote here, what happens? So when it approaches it from the negative side, so from this side here, what happens? So obviously, as x approaches -1, we can see that y approaches infinity because it goes upwards. So what we can do is I can write that in and say y approaches infinity. And then what about when it approaches it from the opposite side? We can see that it goes downwards. And so it's clear that when it does that, it approaches, y approaches negative infinity. Now what about when y approaches the horizontal asymptote at y equals 2? So we can look at this from the different points. So when it comes down this way along there, slightly above that point, you can see that x approaches negative infinity. So I can write negative infinity in there. And then on the other side here, we can see it goes up like that, and it approaches positive infinity. And you'll start to see a pattern with these graphs open up quite often. Now, what about if we had to find the axis intercepts? So we've got to look at when it passes the x and y axis. So what we'll do is we'll say when x equals 0, and we'll just swap for this one. We'll swap fx to y. So we'll say y equals 2, 0 minus 6 over 0 plus 1, which equals -6 over 1, which just equals -6. So it passes through the y-intercept at -6. Now what about when y equals 0? So this would be, focusing only on the numerator, would be when 2x minus 6 equals 0. Therefore when x equals 3. And so it passes through the x-intercept at x equals 3. So if I was to color code this, and I've got that one there, that would be this point here on the graph, so right there. And then in blue, we've got the y equals -6, that would be here on the graph, like that. Alright, so let's do another similar example. So we've got this function now, 4x plus 1 over 2x, 2 minus x, sorry. So what we're going to do is first find the vertical asymptotes. So we can evaluate that as, we will do 4x minus 2 plus 9 over 2 minus x. And I've done x minus 2 instead of 2 minus x at the top for now, simply because we need the positive x. And then what I can do is I can change it to -4 2 minus x, and that'll give us the right for x, plus 9 like that over 2 minus x. And then obviously we can cut out these bits for that one, so just be -4 plus 9 over 2 minus 2 minus x, like that. And so then that gives us, obviously this one, create vertical asymptote of x equals 2 and a horizontal asymptote of y equals -4. Now what we're going to do next is we're going to write the domain. So for this specific scenario, our domain actually works no matter what, because we've got all real numbers here, except for where we have the horizontal and vertical asymptotes. And that's for domain and range. So what I'm going to do is domain, like that, equals, and now pretty little brackets here, x where x doesn't equal 2 because we've already stated that we've got a vertical asymptote there. And then range is very similar, where brackets y where y doesn't equal -4. Pretty simple. Now for the directions, so I can say as x approaches, and I can look at the graph as x approaches 2 from the negative, y will approach infinity as x approaches 2 from the positive, and you'll see that all these kind of descriptions will follow a similar format. Y approaches negative infinity as, I mixed an x there, as x approaches infinity, y will approach -4 from the negative side, and then as x approaches negative infinity, y will approach -4 from the positive side. And then try and fit this up there. When x equals 0, y will equal 1/2, and then where, so don't even need to write when, I'll just say y equals 0. That's an amazing 0. We'll say, just looking at the numerator again, for x plus 1 equals 0. So then it's clear that that'll be x equals -1/4. So that's the points of intercept on the graph. So then what we can do is give ourselves quite a bit of space, draw this graph with arrows and all that, and then we can draw the horizontal asymptote there, which is x equals oh my goodness, -4, and the vertical asymptote, this is easy to do, y equals, well, not y this time, is it? X equals 2. And then for the graph, which I'll do in green, obviously, so we approach that through here, and we know we pass through these 2 points, and it's very tight, but it should be about there, and about, let's just say there, it's pretty close, and so we'll go passing through these points, like that, and then for this side, it just looks like that. Okay, so we've got a bit more of a challenging question here, but I reckon we can break it down and do it. So we've got f of x equals p minus 3x over x squared minus q, where p and q belong to real numbers. Part of the graph of f includes the asymptotes as shown below. And so we've got, it says the equations of the asymptote are x equals 1, x equals -1, and y equals 2. So obviously we've got 2 vertical asymptotes, which you can even see on the graph at -1 and 1, and a horizontal asymptote at -2. And so what we can do is we can reverse the equation a little bit to have a look at a few different values. So what I'm going to do first is I'm going to look at the vertical asymptotes, and we know vertical asymptotes occur when the denominator equals 0. So when x squared minus q squared equals 0, and so this is therefore x squared equals q squared, therefore x equals plus and minus q, because the square roots, the squares will cancel each other out. And so as we know in the question, we have p minus 3x over, what is that, x? 3x over x squared minus q squared. We know that that p, as you know in the other questions where we evaluated it to get a single value to find our horizontal asymptote, in this case we know, because it's already separate, that p will represent our horizontal asymptote. And due to the fact that we've already been provided that, both visually on the graph, and because y equals 2, we can assume that y equals p, which also therefore equals 2. So we know obviously p equals 2 because of that. So then if we can bring this equation down, and also because x equals plus and minus q, and given provided in the question x equals plus and minus 1, then we know finally that q equals 1 and p equals 2. It seems difficult, but when you evaluate it and you look at the different variables, both the numerator and denominator, and you look at the different asymptotes, you can actually find these different parts.